This video we're going to be taking a look at some more properties of limits. And I believe we made it through 5 properties in the previous video, so I'm going to number the first one in this video as 6. And the first property we're going to be taking a look at is the limit as x tends to a of f of x times g of x is equivalent to the limit as x tends to a of f of x times the limit as x tends to a of g of x, and of course provided that these two limits exist, provided that the limit as x tends to a of f of x and the limit as x tends to a of g of x both exist. Okay, so the example we're going to be looking at to use this property is the limit as x tends to 8 of x squared plus 7x plus 10. And hopefully you'll notice that this is easily factorable to x plus 5 times x plus 2. And this property allows us to evaluate the limits of each factor and then multiply them. So evaluating that limit, the limit as x tends to 8 of x plus 5, and multiply that by the limit as x tends to 8 of x plus 2. So we have 8 plus 5 is 13 times 8 plus 2 is 10. So we get 130. And you'll notice this is easier than plugging in 8 here and trying to compute the limit that way. When we split it up into factors, we can plug 8 into each individual factor and then multiply those two results. And that's what this property allows us to do. And there's an analogous property for division. And that's the limit as x tends to a of f of x over g of x is equal to the limit as x tends to a of f of x divided by the limit as x tends to a of g of x. And the stipulations here are, of course, that the limits as x tends to a of f of x and the limit as x tends to a of g of x both exist, but also that the limit of x tends to a of g of x is not 0. And you can see this additional criterion was just added to prevent division by 0. So an example to illustrate that would be this right here. I'm just going to write it down first and then talk about it. So This might confuse you here. You have two separate limits. I thought we only work with problems with one limit. Well, because of this property here, we can actually split this two, or we can combine these two limits into one limit. So the limit as x tends to 5 of x squared plus 5x plus 4 divided by the limit as x tends to 5 of x plus 1, that can be combined into the limit as x tends to 5 of x squared plus 5x plus 4 over x plus 1. And then you'll see this numerator here is factorable into x plus 1 times x plus 4. Denominator is still x plus 1. And we can cancel here, and that's effectively dividing both numerator and denominator by x plus 1. And if you're going to be wondering what about division by 0, well, you'd be dividing by 0 only when x is minus 1, and we're interested in the area around x tending to positive 5. So that won't really be an issue because we're looking at values close to 6. Even if we were looking at values of x close to negative 1, it still wouldn't be an issue because we're not looking at negative 1 itself. So this is equivalent to the limit as x tends to 5 of x plus 4, and that's just 5 plus 4 is 9. So what we did was we really used this property in reverse. And that's something a lot of students need to realize, that a lot of these properties, because of this equal sign, it's equal. It's not just a one-way implication, it's two-way. So you can start with this and that's equal to this, but you can also start with this and that's equal to this. And in this problem we looked at the second case here. And that's something a lot of students I've noticed have trouble with, is if a problem has you use a property in a way that it wasn't originally presented to them, they sometimes get stuck. But before we get stuck, I'm going to move on to the next property here. And that's for some positive integer n, limit as x tends to a of f of x to the n is equivalent to the limit as x tends to a of f of x, and that limit raised to the nth power. And that's provided, of course, that the limit as x tends to a of f of x exists. Now, if we were looking at any integer n, say we also included negative integers, what we'd have to be wary of is that we weren't dividing by 0. So say n were negative 2, then we'd have we'd be looking at 1 over, that would be equivalent to the limit as x tends to a of f of x. That limit raised to the negative second power. So that would be 1 over this limit squared. And if this limit were 0, we'd be dividing by 0. So we'd have to add the additional condition that f of x can't be 0. But let's just restrict ourselves to positive integer for n now. Okay, so let's look at an example. example we'll look at is the limit as x tends to 2 of x squared plus 6 raised to the third power. And this property tells us that that's equivalent to the limit as x tends to 2 of x squared plus 6, and that limit raised to the third power. So we just plug in 2 here, we get 2 squared is 4 plus 6 is 10. 10 to the third is 1,000. Let's say we didn't have this property. What we'd have to do is actually expand this, and this is of the form a plus b cubed, so x squared would be a and 6 would be b, and if you remember from algebra, a plus b cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. So a is x squared, that's x to the 6th. The second term, this is a 3 here. The second term would be 3 times this squared, so 3 times x to the 4th times 6, so 18x to the 4th. And by this term, I'm already sick of this, so thankfully we don't have to expand this whole thing out, because we can find, because of this property here, we can find the limit of what's inside the exponent, evaluate it, and then raise it to that exponent. Raise the limit to that exponent, and that's what we did here to get 1,000. And this is property number 8. So here's property number 9. The limit as x tends to a of the nth root of f of x is the nth root of the limit as x tends to a of f of x and this is provided that this limit exists. So the limit of x as x tends to a of f of x exists, but there's one more condition. If you remember, we can't take even roots of negative numbers. So for example, we can't take the square root of -4, because that wouldn't give you a real value. So we have to add the additional condition that if n is even, then this limit, when as x tends to a of f of x, has to be greater than or equal to 0. And here we're looking at positive integer values of n. For some positive integer n. So when we're just looking at positive integers n, this is equivalent to this, provided this limit exists, and if n happens to be an even positive integer, then what's inside the root has to be greater than or equal to 0. The example we'll look at is the limit as x tends to 1, the square root of 8x squared plus 17. So here, I'll just put a 2 here to make that clear. That's equivalent to the limit of the square root of the limit of what's inside. The limit as x tends to 1 of 8x squared plus 17 is just 25, because 8 times 1 squared is 8 plus 17 is 25. So we have the square root of 25, and that's 5. It's not plus or minus 5 because, remember, by convention square roots are positive. Even though negative 5 squared is 25, the square root of 25 is only positive 5. So this property here allowed us to find the limit of what's inside and then take the square root. And that'll do it for properties. Starting from the next video, we'll just start looking at a bunch of examples that'll hopefully drive home most of these properties and how they're actually used in the algebraic calculation of limits.